So to continue our discussion further into TI-LFA, before we proceed further, we need to spend a little bit of time to understand a few more things, and you would find quite a big of a reference when you are working with TI-LFA is something called P space or the Q space or the P node or the Q node. So if you take a look at the topology or the slide here, which talks about, okay, hey, the P node or the P space is simply a set of nodes reachable from node S. S stands for here source, without using protected link L. So what it says, okay, hey, these are the nodes which you can reach without using a protected link L. And we'll go ahead and explore some of these things more in detail. Q space, on the other hand, is a set of nodes that we can reach the destination D without using protected link. So what is this whole story? What do we mean by here? So the reference to the P space is simply, so whenever we are trying to get our traffic towards our destination. So we have a source, let's say in the case the source is node 1 and the destination is node number 2. So whenever we are trying to get the traffic towards our destination, and anywhere that's going to use that link, so the link in this case, the link between node 1 and 2. So anywhere that's we're going to use this particular link, which we are just simply calling as an L here in the PPT also. And if it uses this link, that's our simply is called as a P space. This is the P space. So that means if this link fails, so if this link happened to fail, it's going to impact our P space. That means now we need to find an alternate way. So we need to find another way to come out of our this P space and still be able to reach our this destination. So the destination is simply our Q space. So just to re-go over one more time, that any time whenever we are trying to send the traffic towards our destination, and when sending the traffic towards our destination, if we are using a link, okay, and that is our protected link. So if anything happens to happen to this protected link, that means it is going to impact our source. So the source that is going to impact, it belongs to your P space, and the destination belongs to the Q space. So now when this kind of failure happens on our protected link, we need to find an alternate path. That's the whole idea behind TI-LFA, right? That we need to find an alternate path and also to avoid the loops at the same time. So now we need to find a way to come out of this P space and still go to the Q space, which is the destination. So that means simply your Q space is the portion. It is basically the portion of the network that does not use this protected link. So that means once we are in the Q space, the system needs no special treatment to reach our destination. So that means the destination is not really dependent on the failure. Okay, hey, what happened to this particular protected link? And whenever we make this decision, from point of view to one of the router, and that router is simply called as PLR. The PLR stands for point of local repair router. So let's go ahead and understand this bit in a little bit more detail before we go ahead and proceed further into our series actually. So let me go ahead and switch to a PPT that I have put together, and then we'll go ahead and talk about what are the different things in this particular PPT. So in this PPT, this is a typical topology that we are planning to use. In this topology, if you see, it's pretty much kind of a ring kind of a topology where we have a 6 router here working. So in these 6 router, we have a node. We are using node R2 as our source node, which belongs into our P space. And then we have a node R6, which is our destination. So destination node belongs to our Q space. And between these nodes, we have a different varying of metric. And if you see, if we have to go with the link state, just simply the hop count, obviously this makes a better path. So now let's say at present, because the hop count is better, the system is using the source to reach this destination node 6. It is using the path via R1, R1 to R6, because that is where we have the least hop count. And the link between R1 and R2 is our protected link. So this is the link that is the protected, and if anything happens to this link, if this link happened to fail, it is going to impact our path which we are reaching towards the destination. And if that failure happens, now we need to find a backup path. So we can go ahead and configure FRR. And in that case, okay, hey, it could find another path and it can go ahead and install that path. But before that path is being installed, we need to understand a couple of the other parameters in this case. So let's say, okay, hey, our protected link, the system was using between the R2 source and R6 destination, this protected link. So this was our protected link. So that means when that link failure happened, it immediately impacted our P space. Now, when it impacted our P space, and if you look at the Q space, the R5 still can go ahead and reach R6 without any worry. Similarly, R1 can go ahead and reach R6 without any worry. That is the whole idea behind the Q space, that Q space is not really dependent on this protected link, but P space is dependent on this protected link. Whenever this protected link failure happens, it impacts our P space. Now we need to do some calculation to find a way to come out of this P space and go inside the Q space, and then from there we want to go ahead and reach our destination. And to do that, whenever these kind of failure happen, whenever the backup path is being calculated, we can go ahead and make use of something called 0 segments, 1 segment, or double segment. And we'll go ahead and explore them a little bit more in detail. So what happens when this failure happened? Now, we need to come out of this P space and still be able to go into the Q space. And that's where we have few other terminologies that comes into the picture. When that failure happened, we have something called Q space that we know. Now there is something called extended P space. Okay, so let's go ahead and understand what is the extended P space first of all mean. And it is the same topology that we were just working. I just wanted to highlight them with the different colors here. So the extended P space simply, okay. So if you look at the R2, which was our source, it was directly connected with R1 and it was also directly connected with the R3. And the protected link, the link that was being protected, that was between router R1 and R2. So the extended P space, so simply the extended P space of the protecting router. So in this case, the protected router is R2. With respect to the protecting link is the union of the P space of the, or if I have to put simply, okay. So extended P space contains the routers basically, okay. So the extended P space contains the router that R2 is direct neighbor. So in this case, the R2 is direct neighbor with R1 and R3. But because the protected link between R1 and R2 failed, so that means R2 is no more a direct neighbor with R1. But R2 is still a direct neighbor with R3. That means R2 can still reach R3 without worrying about this particular link failure, okay. So this link that failed has no problem in terms of reachability between R2 and R3. R3 or R2 can still reach, R3 without looking for this particular failure, okay. And from there, it can go ahead and still reach the rest of the nodes like R4, R5, and then ultimately to R6. So that means the R3 belongs to something called as extended P space. Hey, this node was in the P space. All the direct neighbors which are with our source are simply into the extended P space. But because there is a failure, R1 is not into the extended P space. Now the Q space, let's go ahead and quickly talk about again Q space. Q space contains the router, which is simply the routers, okay, that normally reach our destination, which happens to be the R6 in that case, and without using this link. So that means the link that was used between R1 and R2. So who are the routers that can reach our destination without having to use this failed link? Router R1 can reach. That means router R1 belongs to our Q space. Obviously our router 6, which was our destination, is already in the Q space, as well as our router 4 and the router 5. So that means all these three routers, 4, 5, and 6, they can go ahead and reach R1, R5, and R4 are the routers that belongs to the Q space, because they are not dependent on this link, the protected link, to reach this destination, because they are kind of a neighbor, and this is like a direct neighbor. This is one hop away neighbor. This is also a direct neighbor. So all these three routers, router R1, router number 5, and router number 4, they all belongs to this Q space, and our destination was already into the Q space. So this is simply our Q space. But on the other hand, if you take a look at that, we have also marked router 4 and 5 with the purple color, and that was denoting our extended P space. So the there are nodes in the topology that can act both as a P node as well as a Q node. A router that is both extended in P space as well as in the Q space are simply called as your PQ node. Okay. Any router which is a PQ node can be remote LFA candidate, that is the candidate router to whom R2 can send packets. So if you see, the R2 is capable of sending packet to R4. Hey, it can go ahead and make use of the label for R4 and it can send the traffic via L3. So that means in this case, router 4 and 5, in case R4 and R5 are the PQ nodes, are considered remote LFA candidate. So this is also known as a remote LFA in that particular case. So these are the different type of area or the spaces that we need to keep in mind. There is a P space, which is our source. There's a Q space, which is our destination. Any router that can reach our destination without having to rely on the protected link belongs to the Q space. Any router, our source router that has a direct neighbor, belongs to the extended P space, as well as any neighbor that it can reach with the help of the extended P space. They also belongs to the extended P space, and some router can have both the roles of P router as well as the Q router. So keeping that in mind, let's go back to our slide, and from there we will go ahead and explore some of these things in more details here. So let's go ahead and take a look at this particular example where we say 0 segment. So the whole idea is 0 segment. That means, hey, whatever is already programmed in our label stack, we don't have to use any extra instruction to send the traffic from our source to destination. And that is why it is called a 0 segment example. Hey, we are not programming any special instruction in case that protected link happened to fail. So if you take a look at example, this topology where we have A denoting as our source and Z is our destination. So initially the shortest path, because again we are using the link state protocol, and the shortest path between our source and destination, it is the link between node 1 and 2. So if anything happens to this particular link, so this becomes our protected link. And the link between node 1 and 5 has a metric of 1000, which is pretty high. So that means initially the system will always try to use the link between node 1 and 2 to send the traffic. But if the link between 1 and 2 happens to fail, what happens? So in that case, okay, hey, what is our P space and what is our Q space? So if you simply see the Z already in the Q space, and we said the Q space, the node which can reach our destination directly without having to rely on this failed link, are simply in the Q space. Okay. While there are some nodes which belongs to the extended Q space also. Now in this case we are saying, hey, this is a 0 segment. As I said, we do not have to add any extra information or segment, because what happens initially, let's say if this link fails, the router node 1 don't have to do anything. It just needs to switch the traffic from this link to the other link, and that way it will come out of this P space, and from there router 5 will know how to send the traffic, because the metric between link 1 and 5 is so high that we'll go ahead and use the other links where the default metric is 10. And that's how it will come out of from this particular failure. So if you come back here, let's take a look at initially we are programming the label stack on the source. Hey, we are saying, hey, send the prefix is Z and the packets to Z simply. So when it reaches on node 1, when this failure happened, we are not making any change to this prefix SIDS or to our segment list or to our label stack. The only thing it knows, okay, hey, if that link was failed, it will go ahead and switch the traffic from this interface to the other interface. Now once we reached into this node 5, now node 5 already has, forwarding table programmed to reach our destination Z. And it will go ahead and take a look at, okay, hey, this is where I need to go. And it will go ahead and send the traffic over the node 4, over node 3, node 2 to our destination. And again, why it happened? Because the link cost between the node 1 and 5 is so high that node 5 will never send the traffic back to the node 1. And that is how we are also avoiding any kind of a loops. And for this particular failure or for this particular backup, there was no extra addition of any of the label on any instructions. And whatever the instruction source has sent initially, same were carried out. And that is the reason we are saying, hey, 0 segment. There were no extra segments were added for this kind of a failure to be handled in our topology by TI-LFA. That's the reason it is called 0 segment example. Now let's go ahead and proceed further, and let's take a look at the another example where we are saying single segment example. That means, okay, hey, now when the failure happens, we might need to add one extra label, one extra instruction to our existing list of labels to really divert the traffic. Because see, in this case, all of the links has a default metric of 10. If we, let's say the link between node 1 and again 2 failed, that was our protected link. Now if the node 1 sends the traffic to node 5, because we are using default metric, node 5 has a chance to send the traffic back to node 1 because they all have default same metric, and based on the link state, it has the shortest hop count because hey, it is 1, 2 and 3 simply. So that means node 5 will go ahead and send the traffic back to 1, and then 1 will back send the traffic to 5, and then will go and become an endless loop. So that means now we cannot hand over the traffic from node 1 to node 5 because there are chances that the node 5 might send the traffic back to node 1 because it is less number of hops, end up in creating a loop. So that means now we need to go to a node where once we hand off the traffic, we know it will not go ahead and send the traffic back to node 5. So now we are, instead of sending the traffic to node 5, we are handing off the traffic to node 4. Because if we come from the node 4 perspective, you count based on the LSP 1, 2, 3 and 4. But if you count here 1, 2, 3, that means based on the LSP, the hop count is less on this path. That means if there is a failure happens of this protected link, and if we can add an instruction saying, okay, hey, if there is a failure happened of this protected link, go to node 4. Now to reach node 4, it will definitely go ahead and make use of node 5. And once it reaches node 4 already has a forwarding table programmed, and that knows, okay, how do I need to send the traffic to node Z. So that's why now this node 4 is acting as it is extended P space. That's what it says, okay, it is doing both as a P as well as a Q. So this is our PQ node. And again, if just take a look at example here. Now when initially the traffic was sent from A to Z, the forwarding table or the label stack only had, okay, hey, the prefix set of Z, and the packet was sent to 1. The link failure happened between 1 and 2. Now when the backup path is being installed, we are adding one extra label onto our label stack, and that is the prefix set of node 4. So we are saying, okay, hey, from node 1, do not go to node 5, but go to node 4. And obviously to reach the node 4, it is internally using the node 5. And doing so, when we send the traffic to node 4, now the node 4 will take off the top label, and it is left with the instruction to reach the node Z. And now it already has a forwarding table, and it will go ahead and make use of that forwarding instruction to reach to your destination Z, which belongs to our queue space again. And why? Because once we are on 4, if you count number of hops, 1, 2 and simply 3, and if it needs to go back, it is 1, 2, 3 and 4. So that means we definitely have a longer path, so system will not go ahead and make use of that. And because in this case we had to use one extra instruction or one extra label, that is the reason it is called single segment example. Because to make this to program the correct alternate backup path without causing any loop, we had to tell our node 1, which is our PTR, okay, point of repair, if you PLR, sorry, point of local repair, to say, okay, hey, to reach our destination, first go to node 4, and then from there node 4 knows how to reach our destination. And in that case, that's why we added one extra segment or one extra prefix. It's called as single example or single segment TI-LFA. Now let's go ahead and take a look at a double segment example. So as the name says, double segment, that means we will probably be making use of two labels or two segments to reach or to come out of the P space and or to go to the Q space. That means when the backup path is being programmed, we are making use of two prefixes really to come out of that failure. So if you take a look at in this particular topology, when the link fails between 1 and 2, now if we hand over the traffic to number 4, that's what we are doing here. Now if you count the number of node 1, 2 and 3, and if you see here 1, 2 and 3, 4, obviously what we can go ahead and say, okay, hey, now we are, if you see here, the metric between node 4 and node 3 is so high that if we just simply hand over the traffic to 4, it'll take a look at the metric and it's so high and rest of the link metric is 10. It will probably try to send the traffic from back to 5 to 1 to 2 and to Z, creating a loop. which we do not want. So in that case, we are making use of the double segment or two prefixes. So what are we saying? Okay, hey, first you go to node 4. To go to node 4, that means this is in our P space. So you go to node 4. To go to node 4, we are using the prefix SID. And once you are node 4, to reach the queue space, if you remember, to reach the queue space, we make use of the adjacency SID. So now we are telling, hey, now once you are on this P node or the P space or to the node 4, now go ahead and make use of this adjacency SID to reach into the queue space. And once you are on queue space, the queue space already knows how to forward the traffic correctly to the destination. And that's what we see here. So if you take a look at our label stack, when the traffic was sent from A, we are just making use of a prefix SID where the prefix SID of our destination, and we are sending the traffic to 1. When the protected link failed between 1 and 2, now we are making use of the 2 instructions or the 2 labels. We are telling the node 1, hey, first you go to prefix SID number 4. That means go to node number 4. So once the packet reaches node 4, it will go ahead and take off the top label. Then it look at the next instruction into the stack. So the next instruction into the stack, it says, hey, make use of the adjacency SID between R4 and R3. And using this label or this instruction, it will come to the queue space. And once it reaches the queue space already knows how to resolve or how to reach this particular prefix SID or to destination. And that's how it will route the traffic. And why we had to use this another instruction, because the link cost between 4 and 3 is so high. If we do not go ahead and make use of the second instruction, there is a possibility that node 4 will send the traffic back to node 5, creating a loop. To avoid that, now this time we are making use of 2 instruction or the double segment. So we are telling, hey, when the packet reaches node 1, which is our PLR, again point of local repair, we are programming a backup path, and when the backup path is being programmed, we are making use of 2 segments or 2 instructions. One of the instruction is the prefix SID of the node 4, and that's what we learned, that we make use of the prefix SID to reach our P nodes, and to reach our Q nodes, we make use of the adjacency SID. So once we have reached a P node, from there we are making use of the adjacency SID to reach our Q node, and once we are in the Q space already knows how to reach the destination. That's what we have learned so far. And again, if I go back quickly to the instructions here one more time, and let me go ahead and quickly back it up. That's what we had learned earlier, that P nodes are the nodes reached via prefix SIDs, and that's what we saw on the label stack. To reach the P nodes, we were making use of the prefix SIDs, and to reach a Q node, we use the adjacency SID, and that's what we saw in the last example of the double segment failure primarily. So that kind of, really, I know we have not gone through any kind of hands-on. We will go through the hands-on, but I wanted to make sure you really understand what is a P node, what is a Q node, and how the failure is handled by using 0 segment, 1 segment, or 2 segment. And so far, across majority of the deployment, 2 nodes or 2 segment instruction or double node is the maximum that we have seen. You do not need to use more than 2. And again, TI-LFA can go ahead and make use of the load balancing if it has multiple paths. Again, in this particular example, it shows, okay, hey, we have 2 potential paths and 2 destinations. So yeah, it can go ahead and load balance the traffic across 2 different paths also. So those are the standard things. Again, I would encourage you to spend some time on this particular topic. In the next episode, we will go ahead and do some hands-on around the TI-LFA. So that'll be all for this episode. I will see you guys in next episode. Thank you.